Where's everyone? I don't know. Let me see where.
I don't know. That's what I said. It's like I didn't drop it, I didn't do anything to it. But suddenly I woke up. No, this one like over the social
People connecting issue.
but nothing happened. Like I didn't drop it.
No, it's just over time since DK.
It's 2 years.
Apple. I think they're coming. No. It's recording. No, that's recording. It is recording. Oh, okay.
He did pay for Apple Card. But they did not pay for Apple Card.
Sorry. Okay, so I think everyone knows Michael. He's going to tell us about U, R, G, and E, F, T. Go ahead. Thanks.
Yeah, so I'm going to tell you about some work I did during my PhD with my advisor, Ira Rothstein, based on these two papers. And the way this is going to work is I'm going to overview a formalism for extracting anomalous dimensions of form factors from unitarity cuts. I'm going to talk about how this was extended to the case of the rapidity renormalization group, and I'll explain what that is as well for people who don't know. And then talk about how we can move, kind of apply this formalism a little bit beyond the case of just form factors into more general scattering kinematics, in particular the case of forward scattering. So to kind of start off, I want to quickly talk about form factors. So these are objects that appear in usually some sort of production process where you have some high energy or short distance UV process X that decays into a bunch of outgoing states. And we can, schematically write this as so. And then you typically have like some sort of momentum being injected into this process. And in the case where this is mediated by some sort of UV physics, we typically will resort to some sort of EFT setup where we can write this as some sort of Wilson coefficient, which depends on our UV scale, which I'll just call M here, and some sort of UV IR factorization scale mu, and then some sort of low energy matrix element that contains the dependence on all of these outgoing states, which I'll call F. That also depends on mu as well as P1. Okay. So if we're interested in actually doing calculations of this, well, so there's sort of like two cases that we're sort of interested. One is where we know the UV theory, say if you're doing like some sort of jet physics application, in which case you can calculate these Wilson coefficients explicitly. And then the other case is where if we are trying to probe for new UV physics, like in the case of the standard model EFT, where we can write down what these low energy matrix elements are, but we don't know what the Wilson coefficients might be. But broadly speaking, if we were to able to do the full computation of this, what we would find is that perturbation theory, at least in the gauge theory sector, is plagued by large logarithms of this UV scale to our sort of IR low energy outgoing states, where these SIJs are just the Mandelstems for momenta PI and PJ. And these things can generally be order 1, and so they'll typically need to be resummed if you want to get anything actually useful out of this. what the factorization does is it allows us to sort of split this log up into a piece that just depends on the UV part. And a piece that just depends on our low energy physics that we can observe. And so what we can do is we can derive renormalization group equations that govern the scale dependence of mu in these form factors, or equivalently in these Wilson coefficients. And so typically that's just something simple like this. And then we can solve these, and by solving these equations, that resums all of these logarithms. And so we have well-defined observables that we can then regain calculational control of. Okay, so a lot of like calculational work, particularly in jet physics, and also just more generally goes into sort of calculating these anomalous dimensions, these gamma mu's. And what was noticed in this paper, it's 16. Okay.
So when you say jet physics, what exactly do you have in mind? Like, do you have like DGLAP running, or like
it can be DGLAP running, it can be like pseudocopter pair production, just anything where there's a like transverse momentum dependent form factor, anything where you have like some sort of production process with some sort of outgoing low energy states. So in this paper by Simone Karen Guo and Matthias Wilhelm, what they noticed is that there's actually a little bit better way to calculate these anomalous dimensions rather than just going through the standard renormalization procedure of computing diagrams directly and then absorbing UV divergences into counterterms. And I want to kind of quickly go through their process. But we have our form factor. We can write this as a matrix element as P1, 2. Sorry, that's. So what they said is, let's do something a little bit strange and consider a dilatation by a complex factor of I pi on our form factor. And essentially what this does is it rotates all of our momenta. So that then they become, it essentially takes pi to minus pi.
Are you in a massless theory that's classically scale invariant, or like what's?
No, you're in sort of a in a theory where the mass scales. I guess I should have stated that before. Any masses of our particles is much less than any of our Mandelstam invariants.
You effectively have scalar invariance or no? Like how are you using dilatation?
Yeah, what's the dilatation operator?
So they define the dilatation operator.
Wait, it's not a symmetry of the theory.
No, it's not a symmetry of the theory. And in fact, you can like show in at least in perturbation theory that this is the complex conjugate form factor once you do this complex rotation all your momenta. So the fact that this is how they kind of like define the dilatation, which I assume lines up with the definition that you can write down in a scale invariant theory.
Yeah, it was scale invariant, then we wouldn't get anything.
Yeah, exactly.
And then the thing would be finite, which is exactly what n equals 4 super Yang knows does, the CF2.
Okay.
So that even in n equals 4, there's no trivial dilatation operator for composite operators.
But if the thing was a symmetry, then we wouldn't get any. That's right. I mean, it's a violation of the renormalization is the violation of the dilatation symmetry.
Yeah. I think part of the implication here is that if the dilatation is a symmetry of these form factors, then they have to be real, at least perturbatively. Right? They can't develop an imaginary part in that case. Which seems like
maybe the origin of the trickery is dimensional analysis. He's going to go after the mu square by basically counting the number of log s's.
Yeah, but that's because it's effectively in a massless theory, right? Because otherwise you have mass factors that would violate the scaling.
But when we do renormalization, it's basically the way we do it anyway, right?
Because normally you're interested in the UV. In the
Yes,
UV,
exactly.
you can set things
exactly.
to zero.
so. Yeah, we're gonna essentially ignore
That's right.
the masses altogether. Honestly, this methodology over here does kind of break down in the case where you have massive particles because you miss out on renormalization effects due to masses.
Yeah,
and that does show up.
Yeah.
But standard renormalization, I mean, the way you would do QCD, renormalization of the coupling concepts, so forth.
Yeah. Anyways, once you have this complex conjugate form factor, you apply unitarity, and essentially what that does is it gives you. You can think of it roughly as the S matrix acting on our form factor here. So this basically tells you that once you do this, applying this sort of complex scale transformation is equivalent to acting on your form factor with the S matrix. So then the final trick that Zvi already kind of alluded to is the fact that this form factor by dimensional analysis can really only depend on these Mandelstam variants and our factorization scale mu.
So the S matrix is kind of a time evolution operator, right?
Yes.
So are you saying that dilatation acts like a time evolution somehow for these form factors?
Yeah, in some way. So I think what's happening is that this dilatation is somehow equivalent to time reversal, or maybe time reversal and parity, right? Because if it acts on a position, right, it takes it to minus x mu. So what the S matrix here is doing is essentially implementing that time reversal. If you want to be, if you want to be more explicit, the actual statement of unitarity is, at least at the operator level, something more like this. And then the fact that we have sort of a vacuum initial state allows us to drop this guy here. So yeah, once you use this is sort of, I guess, Lorentz invariance and dimension analysis, then you get that D acting on F. Well, it picks out these Sij's, but that's equivalent to picking out taking minus mu d by d mu. And then by standard renormalization arguments, this is our form factor anomalous dimension. There's this piece corresponding to higher divergences that can show up. And then there's also a beta function piece. So when we kind of put it all back together, what we find out is that we have the following relation. essentially what this tells us is that order by order and perturbation theory are we can extract our anomalous dimensions for our form factor just by computing unitarity cuts. So diagrammatically, we might have this, and then we have a scattering amplitude. Here, so this is some scattering amplitude. This is our form factor, and this goes like our anomalous dimension times our form factor. And this has been used, I think, in a number of places now across the literature by, for example, Zvi and company for understanding the mixing structure of different operators in the standard model EFT, along with some other places. And this is quite a nice calculational tool just because the unitarity cuts are often a lot easier to evaluate than full Feynman diagrams.
So is it something similar for correlation functions? Like you have some kind of semantic equation down there, right? Except you're using it on form factors, yes?
Yes, yeah.
So can I do the same thing for correlation functions or something special happening here then? Like
So the main thing that's happening is the fact that your full theory, like your full form factor with the Wilson coefficient, is just mu independent. And so the Coulomb-Sisbonic equation is just the statement of the mu independence of this combination here. Yeah. So anytime you have like a Argene invariant object that you apply some sort of factorization to, then you can get, then this is the case, yeah. Yeah, I think a lot of times people will just ignore these Wilson coefficients, especially when talking about UV physics. But if you have stuff that's not, UV complete, then usually they will develop some sort of mu dependence. All right, any other questions? Okay. So
Can people use this setup for trying to compute the running, like the D club running, or no?
So in Simone's original paper, he computed the all of the twist two anomalous dimensions using this for splitting functions, collinear splitting functions. Yeah. I think the computation there is a little bit involved, which is maybe why it hasn't taken off more, or maybe just I'm not entirely sure what the reason is, but yeah, he got I think some alternate integral representations compared to the standard approach, and I think he was only able to evaluate them in a couple cases. Yeah, so this formalism is very useful. It does have a couple limitations. So one of the major limitations is that it has this higher anomalous dimension piece that you either have to subtract out by hand or you have to implement some sort of workaround procedure. And that can be a little bit tedious and adds a lot of extra work to take care of. So. A second,
the IR is usually pretty well understood. Like, so if I subtract off, if I know the IR for a given form factor, it's just subtracted off, and I talk about the hard matrix element.
Yeah.
That's fine.
Yes, it's not like a huge issue, but it is just an extra complication. And if you're going to higher orders, sometimes it's actually a lot easier to do the hard computation rather than to do all the IR physics. Is my understanding. I could be a little bit wrong about that, but yeah.
Or some word of perturbation theory. In QCD, it'll definitely get complicated.
Yeah. So the second and probably the more important one is that this it just totally misses any contribution from rapidity logarithms. And if you're not careful, then this can like totally screw up your computation. I think for form factors, this isn't such a big deal, but
Can you say a little more?
Yeah.
Well, yeah, well, what type?
so yeah, so to talk about rapidity logarithms, I need to sort of take a step back and talk about a further factorization we can do on these form factors. So usually what's done is, or what's often done, and particularly in the QCD literature, is that we apply a secondary factorization, where for each outgoing state, we associate to it a collinear matrix element that contains all the physics collinear to your outgoing state. J1, 2, and then there's some background stop function that contains all of the like sort of background low energy adirectional physics. And this is standard factorization stuff. One thing that can happen though is that when we compute these matrix elements and sum them, you get things that look like a large logarithm. So you can have Mandelstam's over some IRCO. So if this is, for example, a massive state or something like that. And even though this looks like a ratio, a ratio of widely separated scales, like something that's UV and something that's IR or low energy. It turns out that when we break this up, we find that this is actually the sum of large ratios of rapidities, which is a little different. So this is so here, n and n bar are just a set of light cone coordinates that you use to sort of talk about these collinear physics. And then nu is a sort of rapidity factorization scale. And all of these elements are sort of a manifestation of the fact that when we perform this factorization here, we're sort of implicitly breaking Lorentz invariance by fixing directions for these collinear matrix elements. And then the fact that we are separating things into collinear physics and in one direction versus collinear physics in another also means that we're breaking boost invariance. And so those two things show up by the appearance of these n's and n bars that come from individual matrix elements, as well as the scale nu. And when we combine everything back together, we end up with our formal boost and Lorentz invariant logarithm, but the individual pieces sort of break that into the intermediate steps. Yeah, so the fact that these logs can be large means that we also need to resum them. And there's a formalism for doing this known as the rapidity renormalization group. And it works almost identically to the standard renormalization group. So our different jet functions develop these new anomalous dimensions now. And then same with our soft function, develops a separate soft anomalous dimension. And then by solving these rapidity RG equations, it allows you to sum these large rapidity logs and return perturbative control again. Just to kind of quickly compare and contrast the rapidity RG with the standard RG. So if we have, kind of going back to our case with these two logarithms, so we have J So this hyperbola is just a hyperbola at fixed invariant mass. So like a fixed p squared, for example. And then the standard mu RG transports us or generates flow along different invariant mass hyperbola. So it takes us from one scale to another. The rapidity RGE, meanwhile, moves us sort of along these invariant mass hyperbolas. So the collinear physics might live over here at this end. So that would be like J. Right. And then our soft function kind of lives somewhere at this intermediate rapidity here. And so by sort of moving us from higher to lower rapidities, it does the same thing as the standard mu RG and allows us to sort of resum these logarithms. Okay, so if we want to sort of, so the goal would be to kind of derive a similar equation to this one now for the rapidity RG, just to get out these new anomalous dimensions. And that would be particularly nice because these things typically, they require additional scales and additional regulators beyond just standard dimensional regularization, and that can complicate computations. So the trick is sort of to do something very similar, where, but yeah, now since instead of doing scale transformations, we're doing like rapidity flow, we replace this dilatation operator with a Lorentz boost in roughly the z direction. And we define it so that it is where we sum over all of our external states and then we perform like a boost in the z direction along each state. And this is, what this essentially does is it keeps things at fixed invariant mass. So this operator on some momentum is just going to sit the same. It's not going to get modified at all. So then what we do is we.
So the z direction is the direction that the thing moves? Like what?
The z direction is roughly the. So in light cone coordinates, kz is. I realize I'm. Far. Is roughly this. So it's just a particular, it's one of the longitudinal directions picked out by your two light cone vectors that you're working with for your computation. So if you were to do if you were to pick, say we were working in the case of only two outgoing projectiles, you might pick n-1. You might pick your two light cone vectors to be this, and then you can see that this just gives you back something proportional to z. So we call it a boost in the z direction. It's not quite that, but it does what it needs to do. Okay. So we take our form factor and then just again restricting to the case of only two outgoing states for the moment. Look at these j's; they're equal. They're some function of new. And that depends on. So they're also like exclusively ratios of our like components and the IR scheme. So what happens is when we apply our boost operator to our form factor, so do to the I pi k bar z, acting on f. This again, by a very, very similar story, takes us to the complex conjugate form factor. But then because we're working with this boost operator and it sees these individual end.p1 and part.p2 components, we can write f is just again equal to this new d by d new operator, which by the rapidity RGE is minus gamma nu I ji. So kind of, yeah.
So, no, I mean, I just kind of, acting on the JI, but on the entire form factor, I mean, its operation seems very obscure to me. As opposed to the one that Simone had. Where
Yeah.
it's like acting uniformly in all of Eventa. So how does
Maybe
it
you
come
can
out
write the
that
formula for P1 is equal to n dot P1, n bar dot P1.
Yeah, maybe that'll make things a little more
Because
clear.
then,
Yeah.
I think it just puts a sign
Yeah.
in front.
Yeah, so you can always, at least for these production form factors, you can always work in the case where.
I guess I'm a little surprised that it just comes out F star, which is what you had before.
So Michael, correct me if I'm wrong, but you just flip the sign in front of each one again.
Yeah, so
Because
your Mandelstam's
Yeah.
Sij, in this factorization setting, they're literally just they'll just do S12. It's just plus things that are like on the much smaller and drop out of the formula. So when you do this boost, it flips the sign of our effective Sijs.
I see, okay.
Yeah.
Okay,
And it's, yeah, the operator is specifically constructed so that it leaves things like pi squared and pj squared alone if you were working with off-shellness as an IR regulator, for example. Because then you wouldn't want to pick up IPIs associated to like ultrasoft modes.
Okay.
Yeah. It's slightly contrived, but it does work as advertised. Yeah, I mean, another way to see that this works is that, again, this is just the time reversal, just like the dilatation was. It's just kind of written out in a weird basis, up to some unitarity transformation.
Like calling it. So the form factor should be a Lorentz invariant quantity. So now you is this supposed to be a Lorentz boost?
So
why does it get something non-trivial?
yeah, it's because again, the individual pieces here.
But you act something under F, the full F.
Yes.
Never mind factorized form, not factorized form. F as a full quantity should be completely Lorentz invariant, but you get something non-trivial.
Mm-hmm. Yeah, I don't remember the exact argument we had.
because
I think
it's written in terms of their
Yeah.
big components, particular directions, like
Yeah.
n and bar.
I-
So if f were only a function of P1 dot Pi dot Ej, then yeah, it's
Yeah.
most invariant because it's just scalar product, but n is a constant vector. 1,0,0,1.
Yeah, you're sort of explicitly breaking Lorentz invariance.
It's
not really the full look.
Yeah.
It's a particular general.
but even on the F, assuming you're trying my subdominant pieces.
Yes.
Okay,
So you're throwing away subdominant pieces.
because otherwise that formula, like
Yeah.
Enrico says, it wouldn't make sense.
The other thing too is that F is technically only invariant under real boosts, whereas here we're doing a complex boost. And so the fact that you're working with a complex boost kind of messes with things a little bit, sort of in concert with all these other statements. So yeah, boosts by complex parameters aren't necessarily guaranteed to be symmetries of the theory.
Your K is not Hermitian, then something.
Yeah, this thing is not Hermitian. Right, it's a anti-unitary operator. I mean, like the dilatation operator, you know, each of the IPID is also not unitary. So sort of going back and putting everything together, we kind of arrive at the final results. Is we get an explicit formula for the rapidity anomalous dimension of our form factor in terms of unitarity hits. I realized I actually left out a crucial piece here that actually probably also explains out a lot of these computations, or a lot of these confusions. There's some hard matching coefficient too that goes in here for physics living above this IR scale. And so the piece that we actually care about is this sort of EFT form factor, or this IR form factor. So maybe I should. Yeah. Sorry about that. That probably, yeah, clears up some of the confusion.
Because on the other side you have including the hard stuff.
Yeah.
Right, like, so because otherwise you could equate these two things and get like some relation between the.
Yeah. No, so the stuff that Simone did with the dilatations really only applies to this hard coefficient piece. This is out any like RG this is out all the rapidity RG structure in the jet and the soft functions. So this is sort of the result that we wanted. And what Ira and I did is we went and we checked this through two loops in a variety of different cases. Like we did the Sudakov form factor with massive and massless external quarks. We also checked the transverse momentum dependent soft function as well. And in both those cases, it reproduced the known rapidity anomalous dimensions up to two loops where we did our computations.
Those results can say like transverse momentum and then like with a massive circle.
No, they're not the same at all. So part of the reason is they they have different IR scales. So in the massive Sudakov, the IR scale is the work masses, and in the TMDs, the scale is like your injected transverse momentum or the Fourier ideal, which is this B squared.
Actually, the region is the rapidity and anomalous dimension was divided by John Connors by using Sudakov resummation from form factor. I had sort of those other things.
Yeah, so there's this funny relation where the rapidity anomalous dimension for the soft function or the TMD soft function in conformal theories is equivalent to the mu anomalous dimension of the Sudakov form factor. But the rapidity and anomalous dimensions for those two objects are not the same. I think they're expected to be closely related, but they do differ by some like crucial terms. Yeah. Yeah, I think the difference in the Wilson line structure is that the Sudakov form factor uses like this V Wilson line, and then the TMDs have this sort of people call it, I guess, the staple shape, where it's got this finite plane segment, and that adds. Okay. Yeah. So now the thing that I want to do, where this sort of story is really probably the most useful, is in the case of forward scattering, where the rapidity RG is much more complicated, as I'll get to in just a second. So the case with forward scattering, right? We have our 2-to-2 scattering amplitude, or I guess cross section if you want. Incoming momentum P1, P2, outgoing P3, P4, and Mandelstam's S, which is and then the forward limit is the case where S is much larger than T, S being positive and T being space-like. And then to keep things perturbative, we work above the QCD scale. So in this sort of soft collinear factorization, you can write down a little bit more complicated factorization theorem for the forward amplitude. So you have is this is be written like this. So you have, rather than one product of factorized matrix elements, you actually have an infinite sum. And these are labeled by the number of essentially T-channel gluon exchanges, which are the so-called Glauber modes, which some of you may have heard me mention.
So this is for gluon scattering,
Yeah,
or
this
do you
is
have
for
proton too?
This is for any sort of gauge theory scattering amplitude for generic projectiles. So I guess the collinear functions will depend on the details of the projectile, but the factorization theorem in general doesn't really care about that. So for some of these higher order matrix elements, they have this complicated mixing structure where two or more T-channel gluon exchanges can mix with operators with different numbers of gluon exchanges. And then all of these operators satisfy, again, a rapidity renormalization group equation. Where you have some anomalous dimension matrix that mixes between all these different operators. This convolution. And then these anomalous dimensions are things that people in the literature have kind of studied since the 50s, I guess since the 80s or 90s. Specifically, gamma 1,1 is called the Regge trajectory. And the other one that people care about or have studied a lot is this gamma 2 anomalous dimension, which corresponds to the what's called the BFKL equation.
So, but you're discussing now leading power factorization, or
Yeah, sorry, this is leading power factorization. So this is a leading power in T over S. Yeah, and then all of these different matrix elements enter at the same order in T over S and QCD, for example. So what we would like to do is just apply this formalism directly to the factorization theorem here and get formulas for the anomalous dimensions in terms of unitarity cuts at the amplitude. The major obstacle is that all of this formalism only works in the case where you have like production form factors. If you have some sort of incoming state that totally kills the whole formalism and it breaks down. And the reason for that is because what this does is that essentially when you have something like log of minus Sij, you can write this as, at least for time like, the positive Sij. As some real part plus an IPi factor. And so this piece, I guess, contains all of the RG information, whereas this piece is computed by unitarity. So in order for your unitarity cuts to get all of your RG information correct, you have to be in this region where you can associate essentially an IPi with every logarithm. And if you have any space-like invariance, then this just totally breaks down. However, there's a workaround here. And the trick is to work with essentially eigenstates of crossing symmetry under S and U. So what people in the literature have done is they have looked at these objects called the amplitudes of positive or negative signature, which are, again, essentially just eigenstates under, they either are invariant or have a sign flip under crossing symmetry. And what you can show is that the negative signature piece is some real function of this combination of logarithms L, which I'll get to in a second. And then the positive piece is some purely imaginary function of this logarithm.
this again, because you're leading power, you have like conservation of helicity flow along the collinear and anti-collinear lines. Because like if you had a plus minus 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 amplitude, you wouldn't have, I guess, this symmetry in the SU exchange, no?
No, you actually still would. So this holds for generic helicities. Actually, the bigger, I think you do have to also flip helicities when you do this sort of crossing argument.
But then it makes us different channels.
Yeah.
Okay.
Yeah, I mean, crossing takes you from one channel to another, so you're not really as far as I can tell, these things aren't really physical. These things aren't really physical amplitudes. They're more like convenient mathematical structures to work with because they have these nice properties. This guy is purely real. This guy is purely imaginary, at least as a function of L. And then L is this crossing symmetric combination of logarithms. So there's a log S over T, log U over T, and then they combine to give you a log with an I pi over 2 rather than an I pi. But essentially, this tells you exactly that all of the logarithms do in fact come with I pi's, although you do have to modify the formula a little bit. But if you look at things carefully and you go through the whole procedure again, you in fact can minus pi r complex boost e to the I pi complex boost on our plus minus signature piece is minus plus our conjugate form factor. And this is sort of the statement that we really want to get to, since now it's just a simple matter of plugging in the factorization formula for here and using unitarity to get back the conjugate form factor, or to get back the amplitude again.
Where was this trick? You said this trick was used by someone else, or?
Yeah, so this was actually done in a different similar paper. So they derived this using dispersive arguments.
That makes sense.
Yeah.
For gamma 1, I thought the log and the I pi were tied together. Is that?
Yeah, so that's what this statement is right here. Is that the log and the I pi are tied together. So gamma 1 only appears in this matrix element, which is here m minus. So that's why the log and the I pi are. Yeah. So one of the unfortunate things about this is that the formula doesn't quite work for the positive signature piece because it picks up the sign flip. And so when you apply this complex boost, you get a slightly different formula where it's related to the real part of the even signature piece rather than the odd. And then there's not really an obvious way to apply unitarity to the real parts. For the odd signature piece, that's not the case. And in fact, if you go through, you can work out this a formula for the Regge trajectory. Minus some type of unitarity cuts, so dagger M. And then you have this subtraction term.
Yeah, sorry, but the guy with the wrong sign, they say the like word. What's wrong? I mean, you have a formula that's correct. It just happens to have another sign in it.
Yes, so it means that you can't extract the anomalous dimensions in terms of unitarity cuts in the same way. So that's the downside. There still is a use to it. Or
it seems like a minor patch would fix it. No, it's just some signs are wrong somewhere.
No, it's because doing this complex boost just introduces an additional sign relative to the form factor case or even the odd signature piece.
So from a computational perspective, like you have to compute the cut integrals, which is the same loop order as computing the say. You just have to change the boundary conditions of differential equations, but the computation is still like a L loop calculation that you have to do, right? So in that sense, well, okay, in one version, you compute the full thing, you take the real part, you take the imaginary part, and extract it from there. And the other one, okay, you write it in terms of cut propagators, but it's still like a L loop calculation. So it's almost as complicated as the full loop integration, no?
I guess that would be true, except that in this sort of setting, when you introduce a unitarity cut, what you're essentially doing is you're replacing a like relativistic softer collinear loop with the Glauber loop. And Glauber loops are generically much easier to compute than softer collinear loops. And so you're actually like reducing the computational complexity of your problem by a significant degree. That, and when you do things in the way people typically do them in these sort of EFT settings with, Feynman diagrams, adding a unitarity cut also heavily restricts what sort of Feynman diagram.
So you do explicit integration. You're not doing like differential equation. You're not solving this in terms of differential equation.
No, the way people do these things, at least to my understanding, it is mostly, or like in this setting, is mostly by doing the integration by hand.
Okay.
That could be different outside of the
that makes like
SET community, but
yeah, because if you think just in terms of reverse unitarity, there's no difference between them, basically.
For us, we add basically an extra insertion of a Glauber operator in that.
I mean, one of the reasons why, at least why we were using it, is it greatly cleans up the by going on shell and using unitarity cuts, it greatly simplifies the objects. And the one thing like we were very interested in was hidden cancellations between diagrams, which became manifest once you did unitarity.
Yeah. Hold on, let me finish writing this formula. So we have this formula. So we have a rigid trajectory in terms of the one piece of this factorization formula, unitarity cuts, and then some subtraction terms, which only depend on the actual logs in these guys. And that's a lot easier to compute than the full amplitude. So in any case, this actually does simplify the computation of the rigid trajectory. And like Ira and I were able to do the full 2-loop calculation of the rigid trajectory sort of by hand, which wouldn't really be possible if we were doing things in the traditional method. So it does simplify a fair bit of work, or it does simplify the computation significantly. The more interesting thing that we find is if we say, take this equation and then take the real part of this guy, there should be I there to project out this unitarity cut, and we take the imaginary part to drop out this real part. So then you get these, what are essentially just constraint equations. So in the even signature, you get this simple equation. And what this allows you to do is if you then plug in the factorization formula and work out all the anomalous dimensions, is that it generates relations between anomalous dimensions of different operators. And that was sort of a surprise. We weren't expecting to find the fact that there seems to be like a lot of additional kind of structure hidden in this factorization formula that's not made manifest here. And in the odd signature, we were able to essentially use these constraints to bootstrap the 2-to-2, or sorry, the gamma 2-2, so the BFKL kernel in the octet color channel, just from knowledge of the tree matrix elements. So
Maybe these are not just like anomalous dimensions that are zero because it's something conservative.
no, these are
Because you get relations between anomalous dimensions of objects if you accidentally split them into things that don't look conserved, but when you combine them, they're actually zero. Like something equals zero.
Yeah, I mean maybe it's something like that. These are really constraints between anomalous dimensions and the actual operators.
For example, sorry?
These are really like relations between the actual operators themselves and the anomalous dimensions. So this guy gives you example that the tree level 2-to-2 or 2-2 operator is essentially equal to the 1-loop 1-1 anomalous dimension, the 1-loop rigid trajectory. And then this piece gives you a much more non-trivial relation if you combine it with this guy. So that the action of this operator on the 2-2, or the 2-2 operator is the rate trajectory squared. And these relations are kind of hard to work with, but they actually do allow you to fully essentially bootstrap what this guy is, even at the level of the convolution, or like the level of the perp momentum convolution. So we were able to basically fully figure out what this guy was just from using knowledge of this piece, and these relations here. So there's like very clearly a lot of extra structure and a lot of these sort of hidden relations between these objects, but we just, we kind of only really scratched the surface on what you can do here. But yeah, it'd be really interesting to kind of explore this further. And also just to use this to do higher order computations. Like the fact that you can just, this gives such like a clean prediction, or like way to extract the Reggie trajectory from even say knowledge of full theory. Full theory's amplitudes expanded in the Reggie limit, plus some like frankly minor computations at on the EFT side. You should be able to start extracting these objects like pretty easily. And that, yeah, the only reason we haven't yet is there's a couple small technical issues. Well, actually, it's with the EFT computation over on this side, but once that's done, or once that's taken care of, it you should be able to push this pretty far, I think. Yeah, I think that's about all I have to say. So.
Can you say something about the nonlinear pieces for the evolution equations? You go beyond BFKL. Can you get like the Politsky-Jim-Block Hamiltonian somehow out of this thing?
Yeah. So the Politsky-Jim-Block Hamiltonian is essentially some sort of basis change on this anomalous dimension matrix, or this factorization theorem, and that kind of ends up mixing this Reggie trajectory piece with the higher order pieces as well. So in this way, at least for like doing computations, the Reggie trajectory, this formalism is a little bit nicer. The other problem with the Politsky-Jim-Block Hamiltonian is in their basis, they keep the logs and the IPIs together all the time. And that's why this was originally derived, was so that they could just throw out extraneous IPIs by absorbing them into the logs. Here, the fact that you have unitarity cuts means you actually want to separate them. And in this formalism, the log comes in this guy, and then the IPIs come in these higher order matrix elements. And that's one of the reasons why this is able to work. If you tried to apply this to the Politsky-Jim-Block, you wouldn't find any mixing. You'd just tell you to take the cut of that particular matrix element, and you wouldn't get any of these additional relations.
Thanks.